Okay, so today just a final exam review. So, no new content today. I understand that there is a relatively interesting World Cup game going on right now, so I appreciate those of you who are here. Those who are not, if you have questions, feel free to send me a note. Just kind of the timeline going forward. Course evaluations are out. I think they disappear Thursday night. It's kind of a weird thing. I don't think they go all the way to Friday. So if you're interested in posting a course evaluation, then the link is actually in the navigation bar of Canvas. So if you just open up Canvas, it's in the top left. So, but otherwise it's there. Today is this final exam review. Wednesday, tomorrow, is when your final projects are due at the end of the day. So, and that will have to be a hard deadline because I need to get the peer reviews assigned. So there is a 10-minute video that you upload to Canvas in the right assignment slot. And then separate from that, a 4-page report that excludes a title page and appendix that you also upload to its appropriate spot. Upload both of those. Those are group assignments. So only one person in your group has to upload them. Once they're all up there, then I will have Canvas assign the peer reviews randomly so that every individual in the class will get a presentation not from their group and a report not from their group. And usually the presentation and reports will be from different groups that they'll have to review by Saturday. So that's due Saturday night. The final exam, 2-stage exam. Formally, the last lecture period is when stage 1 is, but I'm actually opening the availability up window up Wednesday. So you'll have all of Wednesday, all of Thursday, and all of Friday. That means if you do have any kind of last minute questions, get them into me today so I can help you with those, because I'll be very limited in the type of content that I can give, I can give you Wednesday, Thursday, and Friday, because the exam will already be out. But I wanted to give you as much flexibility. I give you 90 minutes online. So it's designed to be a 75-minute exam. You can come into class during the normal class period Thursday if you'd like to take the exam. It's, again, Canvas-based exam, just like the midterm. I'll be here sort of proctoring, but you don't have to. So you could start at any time, Wednesday, Thursday, or Friday. And once you start it, you got 90 minutes to complete it. Then during finals week, the collaborative stage 2. So formally speaking, I will be here Thursday of finals week in our exam slot, which I think is on Canvas, and I forget it off the top of my head which one it is. But what I've done for stage 2 is I've made the availability all of finals week, all of the working week of finals week, Monday, Tuesday, Wednesday, Thursday, Friday. So you'll be able to start stage 2 whenever you want, starting Monday, so long as you submit it by Friday. If you submit it multiple times, the latest submission will be the one that's graded. So if you want to keep it up, throughout the week and then submit finally at the end, that's fine. If you submit it and then realize you want to make a mistake, or you made a mistake and want to resubmit, that's fine. Just know that your resubmission will be the one that gets graded, not your original one. So you get 3 days to start the 90-minute stage 1, Wednesday, Thursday, or Friday of this week. And then you got all 5 days of next week to do stage 2, though I will be here during our final exam period, which I think I have posted on Canvas. I don't know off the top of my head which bracket it is, but it's the standard time window for classes on Tuesday, Thursday at 1:30. And so I'll be here in case you want to come to this classroom and work together on your stage 2, but you don't have to. So any questions about this timeline? I'm going to back up and see if there's any questions online as well. I see a question online, and I think it was probably posted before I said it, but stage 1's availability is Wednesday, Thursday, or Friday. So it is marked as being due Thursday night, I think, but it's the same thing as any other availability window in this class. As long as you get it in under the availability window, you'll get credit for it. So you can have until basically through Friday night. So now once Canvas sees you've gone past the due date, it'll automatically give you a 0. And I just have it do that as an extra reminder that, oh, by the way, the thing that I was expecting you to do by Thursday night, you didn't do, just so then you have Friday then to go back and take it. So if Canvas automatically gives you a 0, but I've hidden the grades, you're not even going to be able to see that. But you'll have still Friday to do that. So, so yeah, all of Wednesday, Thursday, Friday, you can submit it. It's technically due Thursday night, but if you want to start it Friday, that's fine as well. Similar with the stage 2. And then, like I was just saying, your grades will be hidden until stage 2 is done. So you won't see the answers to stage 1 or stage 2. You won't see your grades at stage 1 or stage 2 until after finals week. Any other questions, online or in person? There's a question, is there a lab section tomorrow for last minute project questions? I can email the TA to see what his plans are. I mean, we formally have the lab period there Wednesday, and so that's certainly available, but I haven't checked with the TA on how many people have been coming to lab. I've left it kind of up to him that if nobody's coming to the lab period, then as long as he makes it clear, then it doesn't have to be always available. But if there is a need for there to be sort of a standing office hour there for last minute project help, then I will ask him to be there for sure Wednesday. Any other questions? Okay. All right. Final project reminders. This is just, that when you're submitting your report, make sure it's got the right sections. It's only 4 pages long. There's a final report document which goes into this in a little bit more detail. There are sample final reports online, but note that I changed the format just a little bit a couple of years ago. So some of the sample reports are in an old format that aren't necessarily, like, some of these sections have slightly different names or in different orders, but they have all the same content. I just moved them around to make them easier to grade. So other things like, what do you need to show? I mean, the point of this project is to tell me a story about operations that requires you to use a simulation to really be convincing. So if it's something that you could justify without the sim ahead of time, then maybe you need to drill down a little bit more into the sim. If your sim is complex enough that it has enough parts that you effectively sort of kind of need a submodel, that's a good sign. But the bigger point is, like, you really want to say, I have an idea for, this is one example. I have an idea for a way to redesign a particular operation. I have built a sim of how it is now. I have built a sim of my idea. I do a test on them and I find either a significant difference in performance or a non-significant difference in performance with a tight confidence interval. And if you've got you got either of those, I've shown a difference in performance, or I've shown they don't differ in performance and the confidence interval is tight, then that tells me that, either your idea worked or your idea didn't work. Either one of those is a fine result. The goal for this class is not to find performance optimization. The goal for this class is to use simulation to answer the question of whether a performance optimization actually worked. And if it didn't work, that's fine. But because you didn't know that it didn't work until you ran the sim. So it's a success. So the sim is giving us knowledge we didn't have. That's the goal of the project. All right. Any other questions about the project stuff? Okay. And then double check questions online. Okay. All right, so final exam basic outline, just like the midterm, automatically graded exam, Canvas exam. So you can kind of think of it, it's similar to a Scantron exam. 2-stage exam, as we all know, we're familiar with after the midterm. Stage 1 is 80% of the score. It's designed to fit within a 75-minute period. I've actually sort of designed it so that most people, like, the average timing will probably be closer to 30 or 40 minutes. So some people will finish it in 20, some people will take an hour. I think very few people will take the full 75, but again, I give you 90 just for technical issues. Closed book, closed notes, two-sided handwritten formula sheets are allowed. You can type them, but you can't photocopy or similarly reproduce from books and etc. So it has to be kind of hand produced. The stage 2 next week, 20% score, collaborative, open book, open notes, open Canvas, can collaborate with other people enrolled in the class currently. You can use, like I said, Canvas. I don't want you to use other internet resources. I don't want you to receive assistance from anyone outside of the current class. But if you want to collaborate through Slack or Discord, et cetera, with each other, that's fine. You can use those collaboration tools, but I just don't want you to use other information sources outside of the ones that are provided or that you've taken notes or your classmates. If you need to, you can use Arena. You can open up Arena and use its help files and things like that. That would be also a fine thing. So, so any questions about the general format? Again, this is just like the midterm. And for those who didn't hear it before, stage 1 will be available Wednesday, Thursday, Friday. Stage 2, Monday, Tuesday, Wednesday, Thursday, Friday. So stage 1, the bottom half of this week. Stage 2, all of the work days of finals week. Okay. It's a very similar exam setup as the midterm. So, and I've got sample final exams online for you to look at. Basically, when I build the final exam, what I'm shooting for here is, to start out with a bunch of concept questions. They're typically going to be multiple choice or matching. So questions about, DES fundamentals and models, questions about probability distributions, which probability distribution to use for which input, questions about methods, when to use a QQ plot, when to use a PP plot, those sorts of things, distinction between steady state and terminating systems, output validation, performance estimation, confidence intervals. You can imagine a lot of like concepts type of things, like which variance reduction technique does X or does Y, and you'll have to choose between, these 4. And then some Arena basics. So that's kind of maybe a new thing, is that do expect to see maybe a diagram. I'm not going to ask you like, under which menu do you find something in Arena, but I will maybe show you a flow chart of a process. And I might say, assuming that you wanted to edit the inter-arrival time distribution for this queuing system, which block would you go to update the inter-arrival distribution? And you'd have to say, well, that's the create block or something like that. So that's the type of thing. Do you know roughly where to find things and how to understand the flow of a simulation model? Then, maybe some short problems. So, maybe a statistical power problem, maybe do an antikinetic variate or a common random numbers problem, maybe calculate some confidence intervals, maybe figure out, given a confidence interval, how many more replications you need to meet particular confidence interval constraints, those sorts of things. So a little numerical stuff. There might be some Arena there, kind of similar to that Arena problem that I had on the midterm, where it had to do with knowing the syntax of the disk, the discrete function. Well, similarly, so you should know basically how to use disk, expo, random number streams, those sorts of things, the kind of Arena basics. So that if you had to walk up to an expression field in Arena, you would know what to do or where to go with that. Statistical tests, though, you could expect to see like a chi-squared test, but the chi-squared test probably won't be testing uniformity. It'll be testing a more generic distribution, kind of like that homework you've done. Maybe a power analysis of a one sample t-test, like the homework you've done. Hypothesis tests of relative performance. So, generate a confidence interval and compare it to, like, does this confidence interval indicate that this hypothesis was rejected or not? Those sorts of things. And then maybe a design problem. So random variate generators, remember those. That was kind of a pre-midterm topic, but it's really important. It's important you leave this class knowing the inverse transform method. So can you do the inverse transform method? Do you really understand what's going on in the inverse transform method? Then, that's, maybe go back and review that, because that could pop up as well. And where do you find other resources? So that's the basic outline. Like I said, there's, there was a practice ICAs, both for pre-midterm and post-midterm content that are available. There's sample midterm and final exams and solution sets on Canvas. Keep in mind that some of the final exam samples that I've provided are from previous semesters where I wasn't doing a stage 2. So they actually were meant to take 110 minutes. And so for those final exams, they're probably longer than what you'd expect. So this final exam is like probably going to be like 35 points or something like that, really similar to the midterm. So it's similar length in type as the midterm. Homeworks to study, homeworks D2 and G3, C2, those are kind of good ones to look back on. Try to remember how to do hand simulation. So expect me to maybe give you a hand simulation table with stuff left out and you have to fill in the right things or answer questions about the hand simulation table. The bias issues that were brought up in homework J2 about how if you don't initialize the steady state simulation correctly, you can get bias in the steady state estimates. There are some additional problems that you might want to review from a textbook. And so if you review these I think would be a good practice for the final exam. And there is in the final exam module some solutions to some of these that have already been posted. So a bunch of resources online for studying. Other resources, if you write in the modules, every lecture has a chapter associated with it. And so if something really wasn't hitting when I gave it to you and sort of in lecture B1, just remember that I've said, well, see how the book does it. Maybe the book does it a better way than I do it, and that provides you another resource. So any questions about the layout or where to find resources? See if there's any more questions online. There's a question, will the exam be arena-based? There will be, like I said, you should expect at least a few arena-based questions. Again, I'm not expecting you to know where to find things in arena, like where's the replication set up and those sorts of things. But if I give you an arena model, be able to read the model and kind of know what each block does, what's included in each block, how to reconfigure the blocks if you need to change the sim. And I think there are plenty of samples of that. So if you look at the final exam, the sample final exams online, you can see kind of the types of arena-based questions that I asked. Okay. Other questions? I think the rest of what I've got here is basically just the greatest hits from the sort of the presentations back from the beginning of the class all the way up to the latest lecture. I can walk through these or I can stop now. If you have specific questions, if you have things that you would like me to, like I've got the tablet up and so I can work a problem if you'd like to see a review of a certain type of problem, or if you have specific questions, I can answer those now, or I can just start going through these and as questions come up, you can raise a hand and let me know. So are there any burning questions that somebody wants answered right now before the midterm or the final exam window opens up tomorrow? Or questions online? Yeah. I don't recall it on the exact wording, but the motivation behind J2 was that is that if the inventory level started at 0, for example, that's totally unrealistic because you wouldn't keep a standing inventory level at 0. And so so as you run the sim, the inventory level will rise up to somewhere close to its steady state. And so what you were supposed to see is that as you initialize it and don't have any sort of the warm-up period that gets rid of that data, if you initialize it, include all of that inventory data, then what you'll find if you were to take average inventory or something, or even see like how often, I forget the stats that I asked you specifically about, but the lower the inventory or the farther the inventory was away from its steady state, then you should have seen the output kind of drift away. Like, so there was a significant impact of where you set the initial conditions. And so what you're supposed to get from that is it was a terminating system, then you better make sure you set the initial condition in the correct spot, or else you're just going to get the wrong output. But if it is more likely a non-terminating system, and so it's a steady state simulation, then you better either set that initial condition close to its steady state, or or use a warm-up period to get rid of all those initial transients, because they're going to really bias the outputs. That was kind of what I was hoping you were getting out of that exercise. Does that make sense? Other questions? And like I said, I can just start going through this and you just feel free to interrupt me, because yeah. Yeah, so there's verification, validation, calibration, and just general testing. So a lot of times it's all bundled under V&V or TV&V. The big distinction I would want you to make is that verification is the process of debugging your sim. It's not, so like when I look at a model, a real system, I get an idea of what I want to put into my arena model. That's one thing. But then when I start building my arena model, sometimes I just mess up. And verification is looking for those bugs in your model. It's not, there may be no problem with how my general idea for the model, but I've just used the wrong syntax, or I put things in the wrong place or something like that. So I just didn't use arena correctly. So verification is verifying that your arena model is running the way you expect it to run. So I expected to have exponential inter-arrival times with 1 minute on average in between each person. And so when I run my sim, I might want to take data on the inter-arrival times just to make sure that I put those in right with the right units or something like that. So if it comes out that it's actually got an hour between every, I said, well, I didn't want an hour in between, I wanted a minute. So that would show me that that's not. So verification is more debugging. Validation is sort of a higher level debugging, where it's like, is my fundamental idea about this model, does it actually mesh with the real world? And so I assumed an exponential inter-arrival times. Well, it turns out that actually the inter-arrival times of the real system are not exponentially distributed. So what I really need there is something that's log normal distributed or something like that. So those updates, validation catches these fundamental mismatches between the real world and in my model. And it's not about the coding, it's about like the code you've chosen to write. It's not about whether you wrote it right, but it's whether like what you chose to write. And the process of fixing your model is calibration. So all of that we find is involved in testing. So that's why we often just call it TV&V, testing, verification, and validation, or just V&V for short. And so that's just the general process of fixing my bugs, updating my model to match reality, and that process of updating is often calibration, which is increasing the caliber of my model, where the term calibration comes from. Does that make sense? All those? Yeah. Yeah. No, the tests you should really focus on are chi-squared, KS, t-test, and like paired t-tests. And then the kind of, when we got into the two sample things, we started generating those confidence intervals, like the different type of two sample tests, like the pooled variance, the unpooled variance, and the paired difference again. So those are ones that sort of focus on. You should know that the reason why other tests exist. You don't have to know what the Anderson-Darling test is, but because the Anderson-Darling test fundamentally is kind of a competitor of the chi-squared test, but it provides higher power. So that's the big thing. Like, as long as you understand that, like, sometimes we need a higher powered test, but there's risks of a higher powered test because a high powered test will reject everything if we have too much data. So know that those general ideas. So the tests I listed, those are the ones you're going to know in detail, and know that other tests exist for special purposes or higher power, like Shapiro-Wilk. Like, I'm not expecting you to remember that Shapiro-Wilk is a high power test for normality, but But that's an example that, you know, that if I really need to make sure that a small number of samples are normally distributed, I need a high-powered test specifically for normality, and such a test exists. It's Shapiro-Wilk. So know the motivations behind why other tests exist, but the tests you really will need to actually do work on the test are those ones that I just listed. Yeah. Oh, Bonferroni correction. Yeah, I would say you should know that. So that, you should know that if you're doing a bunch of pairwise comparisons, you need to count all of the comparisons that you plan to do, divide your alpha by that number of comparisons, and then do the comparisons with that tinier alpha. So definitely know that, because like that's so important to simulation. It's so easy to fish when you've got like 100 outputs that you can compare across. So definitely know Bonferroni correction. Other questions? Questions in the chat, online. All right, well, as questions go, just raise a hand, you know, this is just meant to kind of be an appetizer. So it could be something I passed, or it could be something I haven't hit before, and that's totally fine. So going back to the beginning of the semester, stuff you want to re-remember, and something that's almost a little bit more philosophical, like, you know, what are models? And I was saying that my general definition that we use in this class, that models are anything that can answer a what if question. So models do not have to be simulation. They don't have to use formulas. They don't have to have math. They just have to help you answer a what if question. So you might not know how a kiosk might work, a hypothetical kiosk might work at Panda Express because they don't have kiosks there. But you've seen kiosks at McDonald's. Well, McDonald's can be a model to answer the what if question for how would kiosks work at Panda Express. So McDonald's itself could be a physical model that may not, you know, be perfect. All models are wrong, but it still could be useful, because you want to know how long does it take people to stand at a kiosk? Well, let's go to a place that's implemented kiosks and see how long they stand there. And that will be my model for how long they might stay there in the hypothetical case of a Panda Express kiosk. So, I'm just trying to drive home this point. This would be an easy multiple choice question or a true false question. Models don't have to have math. Models don't have to have sim. Models are defined by what they do and not what they're made of. They answer what if questions. The particular models that we do study a lot of in this class are simulation models. So make sure you know all your discrete event simulation fundamentals. So, you know, entities, attributes, resources, state variables, state, clock, events, activities, delays, the event calendar, you know, all of these fundamentals. Make sure that you know those distinctions. Make sure you can read a simulation table, a sim output here. So if I can give you one of these, and I oftentimes, just for simplicity, if I was to give you one of these, it will be kind of related to this one that you've done in the homework. So I can't guarantee that it will be an MM1 type system, but you know, it might be an MM2 or an MM3, but the idea is that it'll probably have inputs coming into some servers that have some capacity, so that you can generate a table that looks like this, which will have a queue length, a server length, a checkout line, or something like a checkout line, and a future event list, and be able to process through that. So make sure you can do the hand simulation. And a symbol, you know, and know things like the difference between activities and delays. So any questions about those those kind of like the very first things we covered? Okay. Moving on, probability stuff. So, you know, probabilistic input models. In order for us to talk about probabilistic models, we have to know about probability mass functions, probability density functions, cumulative distribution functions. We have to know about means, expected value, variance, standard deviation. Know some of our common distributions. Yeah, I would say know what a quantile function is. That's not included in the moments that we talk about under probability, but a quantile is an important it is an important stat about a distribution. So I would definitely say know what a quantile is and what it represents and those sorts of things. If I were to give you 100 data points that were sorted, could you, pick out the 50th percentile or something like that? Know some common distributions. Again, I'll have a table of those here in a second. The basic parameters and the common uses. So again, I think I have a table of those here, which I'll get to in a second here. But and the basic idea behind input modeling really is what we're getting at here. So know that stochastic is not a synonym for random. Stochastic is an approach that makes a guess or a conjecture, that we can use randomness as a source of variation, even if the real system we're modeling is not random. So a stochastic model will use randomness, but stochasticity is more about the use of randomness in the place of possibly deterministic processes that are behind the scenes. So that's the kind of idea here. So it's stochasticity is not a synonym for randomness. A stochastic model uses randomness, but those two are not interchangeable terms. Input modeling is the process of selecting probability models for those stochastic models that mimic realistic variation. So know that the inputs are not synonyms for entities. Inputs are the probabilistic models that go into the sims. The entities are just like water running through a fountain. The shape of the fountain is more like the input. So the input sort of determines how quickly the entities arrive and depart, but the inputs are not the entities themselves. The inputs are the probability distributions. So any questions about those distinctions? They're kind of like fundamentals. Again, easy multiple choice questions. I definitely will draw one or two questions off of this slide. Okay. All right, I mentioned, know these distributions, uniform, triangular, normal, exponential or along K, and Weibull. Those are the continuous ones. Know some of the basic uses of those, like know that, use uniform when all you know is a lower bound and an upper bound. Know that a normal distribution is unbounded, and we typically use it when we're modeling additive processes. Know that an exponential has to do with like independent interarrivals. And if you have a sum of exponentials, it's an Erlang K, which causes the distribution to get a little bit more hump-shaped. Another hump-shaped kind of relative of the exponential is the Weibull. So Weibull distributions typically used for failure times, but you can also use exponentials for failure times. So if there's a constant failure rate, it's an exponential. But if it deviates from a constant failure rate, so most of your failures are late or most of your failures are early, then a Weibull allows you to bend the distribution to accommodate that deviation. So it's a flexible failure distribution. So those are your continuous ones. On the discrete side, know that a Poisson is discrete, for one. It's a count of exponentially distributed interarrivals, basically. So if I have things arriving with exponential times in between them, the count of them that arrive in an interval is Poisson. Then on the flip side of that, Bernoulli binomial, negative binomial, and geometric, these are all based on kind of the weighted coin that comes up heads with probability P. So, that's our Bernoulli trial. So, know that if I, know that I'm flipping in coins with this weight, the binomial is how many of them come up heads. Know that the negative binomial is how many tosses I need until I get a particular number of heads. Know that the geometric is a special case of the negative binomial, where it's how many tosses I need until I get one head. So those are kind of the ones that I really want you to know coming out of this class. And then know Poisson counting process. So the Poisson counting process is kind of a bundle of kind of Poisson and exponential together. So, when we're describing things, random variables over time, like we can say how many people arrived at the store after 1 minute, after 2 minutes, after 3 minutes, after 4 minutes. Well, each one of those time instances is a different random variable. Each one of those time instances is a different Poisson random variable. And so a Poisson counting process is a collection of Poisson random variables representing how many people arrive after a particular duration, where that duration is what indexes the different Poisson variables. And then those are related then to exponential, because a Poisson counting process is also associated with exponential inter-arrivals. And so that's kind of like just a fundamental connection between Poisson and exponential. Poisson is how many exponential inter-arrivals occur in any particular interval. So be able to flip from a Poisson mean to a exponential rate just by dividing by the interval over which the Poisson is defined. So if you get 5 inter-arrivals in 10 minutes, then the exponential rate is going to be 5 arrivals divided by 10, so half of arrival per minute. So there's those sorts of things. You don't have to worry about merge processes and split processes. I end up not talking about those that much, so I'm not going to ask about those sorts of things. And that's really kind of 470 material anyway. So any questions about our distributions, about our key input models here? So when we talk about input models, we're talking about choosing distributions like these to go into our sims. Okay, questions online? Okay. And this is just an, I think, extension to that. So if you're looking for kind of a cheat sheet here, I've just taken the ones from here and then expanded out kind of an explanation of each one of them. There's the discrete versions. So yeah, so that's probability. Okay, any other questions about probability and input models? All right, so then the other thing we have to remember is how to generate random numbers and how to generate random variates. So pseudo-random number concepts. So the biggest things I want you to know is the general idea of using seeds to generate independent random number streams. So you have a mathematical function that will generate a sequence of numbers. And if you seed it differently, the sequence of numbers from one seed will be independent of the sequence of numbers from another seed. And that's how we generate independent replications in a simulation. And so that's why it's kind of important to seeds there. The required properties, that's the independence and uniformity. So random numbers, remember when I talk about random number, that's a random variable uniformly distributed between 0 and 1. So this term random number has a very special meaning in this class. Random variate is the general, like an exponential random variate, that's exponentially distributed. But a random number unless I say otherwise, is you can always assume that that is uniformly distributed between 0 and 1. And so uniformity and independence will be our required properties. And then we've listed a couple of desired properties. We want it to be fast, reproducible, etc. Know how to use a linear congruential generator. So if I give you a multiplier, the offset, and a seed, that you'd be able to calculate out, the next number in a sequence. You don't then know that a linear congruential generator has an issue with generating long sequences before repeating, and so we can use combined linear congruential generators to generate even longer sequences. Kind of the point behind that. Once we have these random numbers uniformly distributed between 0 and 1, we can have a computer transform them into random variates for any distribution. So know a basic understanding about these random variate generator expressions, how they can be used, know the inverse transform method. So if I gave you a piecewise probability density function, like you've done on homework, like you did on the midterm, could you turn that into a cumulative distribution function and then invert the cumulative distribution function? Make sure you know, like when you invert a square, you have to deal with the plus or minus of the square root in the appropriate way. And then, empirical commutative distribution functions and disk and content arena. So know that if I give you a bunch of data that you can't fit, you can actually load the data as empirical CDF into the disk function. And then if you'd like to interpolate, you can just change the disk to a cont, is the discussion we kind of made there. So those are kind of the things you want to know from random variate generation. And I think I just summarized some of those things here. So this is our random number generation, just reminding you of the stuff I just said. Here's our linear congruential generator. Here's our inverse transform method explained pictorially. Here is it kind of the process broken out. This is how to use it for discrete random variables and the empirical stuff down here. And that's basically it. So any questions about random variate generation? It's kind of like the last pre-midterm topic. Questions online? Okay. So, this little refresher we did, so hopefully now at this point in the class, if I were to ask you which one of these is a PDF, a CDF, or maybe even a quantile function, which one could you sort of pick out here? So hopefully when you look at these, you can think, well, since this one starts at 0 and rises to 1, it must be a CDF. This one here, I'm not sure what it is, but the area underneath it looks like it's probably about 1. So it's maybe a probability density function. And this one looks like it's maybe the inverse of a CDF. So it's a quantile function. So I can tell that because its x-axis goes from 0 to 1 and its y-axis is it's unconstrained. So be able to sort of, be able to look at these things and call out which ones they are. Similarly, other examples here, I would call that my CDF. I would look at this one and say that looks more like probability density function. I would say this looks like a quantile function, an inverted version of a CDF here, because again, 0 to 1 on the x-axis, and it doesn't matter what it is on the y-axis. And this isn't even a function because one of the x-axis maps to two things on the y-axis, and so that's other, nothing. So any questions about these density functions, CDFs, quantile functions? Yeah. Yes. I'll double check. Have you completed the compliance test? Yeah. Yeah, so in order to get access to the final exam module, make sure you take that little 1-question compliance test ahead of time, and that should unlock the resources in that final exam module, just like the midterm. Other questions? There's a question online, what exactly is a variate? A variate is, so a random variable is like a general term, like an exponential random variable is something that is exponentially distributed. A variate is a realization of an exponential random variable. It's actually a number that was drawn from the exponential distribution. So a random number is what I would call a uniform variate. So it was drawn from the uniform distribution from 0 to 1. And so I would call it a variate because it's actually drawn from that distribution. And so when we say generate a variate, what we mean is, draw from a distribution, generate a random number. And we can refer to variates coming out of simulations too, like an antithetic variate. We talk about AVs and variance reduction techniques. That is, you run one simulation, you run it again with its complementary numbers, you add both of their outputs together, and then you get a new output. And that output we refer to as an antithetic variate. It's a variate because it was drawn kind of randomly from the distribution that came from the average of 2 of our simulations. So a variate is just a realization of a particular random distribution. I hope that makes sense. Any other questions? Okay. All right, and then so post midterm, we got a lot into sort of the stats of things. So I want you to know what this receiver operator characteristic curve is, this ROC curve, which basically is just plots type 1 error alpha against statistical power, which is 1 minus beta. So I want you to know that as you increase the alpha of a test, you are necessarily going to increase its power as well. And so there's a fundamental trade-off there. You can't ever have high power and low alpha because the two are linked together. And so the best you can do is have a statistical test that follows this bent line here. And you want that bend to be as high as possible. And so good statistical tests, high-powered statistical tests will have almost, this relationship between alpha and power will almost look like a right angle. And so that's like the ideal. And if you have if you draw a lot of samples, then that's what it's going to look like. The more samples you get, then the more kind of bent up this will be. The less samples you get, or you get closer to just flipping a coin who's weighted to be your alpha. So if you have an unfair coin whose heads probability is your alpha, you can flip that whenever you want to do your hypothesis test without relating to any of your data, and you would get this line right here between your alpha and your statistical power. And this relationship is just set up by this picture where we've got our true negative, our a true positive, and the way those two distributions lay on top of each other. And we set some critical value, which has to do with the tail of our true negative distribution, but it's also going to catch some things in the true positive distribution, and that's what generates those errors, the false positives and the false negatives. So hopefully this slide is starting to make some sense. And so knowing the qualitative features of this slide, being able to identify the true positives and true negatives and false positives and false negatives in this diagram would be an important thing to know. Being able to understand the general shape of the ROC curve and how it's modeling alpha versus power or 1 minus beta, that's another good thing to know. So any questions about this depiction or the concepts on this slide? Okay. Related to all of that, understand this table here, which, if we've got the null hypothesis down this column, or the world as expected is another way to say it. And we've got when our null hypothesis is not true down this column, or otherwise the world is different from expected. So in this case, we're saying a positive result is the detection of a difference from expectation. So detecting a difference from null is detecting a difference from the world as expected. And so the world as expected for your final projects might be your as-is simulation. The world is different would be, well, is my proposed change different from the as-is model? If you can detect a difference, then that's great. Then that indicates you've made an improvement, but you don't want that to be a false positive. And so a false positive would be, I've produced a single simulation run where my proposed system does better, but in reality, that was just lucky. And under most cases, the proposed system does pretty much just as well or even worse as the as-is system. So just understanding this table here, this kind of confusion matrix where positive results are the detection of variations from the null. So yeah, know what it means to reject the null, understand the relationship between type 2 error, statistical power, so that's beta type 2 error, and effect size, understand the relation between standard deviation, standard error, confidence intervals, and prediction intervals. So these kind of key statistical concepts. Any questions? Any stats questions? Okay. So then we, input modeling, picking the input models. So, drawing a histogram, being able to read a histogram, being able to sort of say what histogram is sort of well binned and not, choosing candidate distributions. Is it discrete? Is it continuous? Let's match the shape. Let's do QQ plots and PP plots. Do the QQ plot first and then the PP plot. And that generally fits our shape. You know, as I mentioned before, these are discrete distributions that are generally useful to know. I listed more than I asked you for before. So these are in general continuous distributions that I'm not expecting you to know all of these, know the ones that I talked about before, but just know there are a bunch of continuous distributions and a bunch of discrete distributions that all are possibilities. But if you can't find a distribution that fits your data well, and you can't break your data up into sub-distributions that make sense, then you've got the data-driven last resort of the empirical disk and empirical Kant that you can implement in ARENA. So, and this is just going over stuff that I've kind of already talked about, you know, normal distribution, when to use it, how to implement it in ARENA, exponential, same thing, Weibull, same thing, already sort of chatted about that, Poisson, same thing. QQ plot versus PP plot, do the QQ plot first, and then the PP plot. It's kind of all it's going to be summarized here. And then we move on to point estimation and then interval estimation. So any questions about any of this so far? Questions online? Okay. So moving into point estimation, so know that a summary statistic is just taking data about, or taking a summary of data you have. They're not related necessarily to any distribution. So, you know, taking mean of continuous data or means of discrete data. Know that when you take a variance, if you estimate the population mean from the data and you don't know it ahead of time, you've got to use this n-1 to calculate variance in both of these. Once we have those sample statistics, that helps us sort of understand, you know, basic features of our data. But if we then suspect that our data come from a particular distribution, Poisson, exponential, or whatever, understand the basic idea behind maximum likelihood estimation, that we can optimize for the parameters for which it is sort of most likely that those data would have been drawn, that those data would be variants that would come from that distribution. And so, and that there are maximum likelihood estimators out there. So if I ask you to do an MLE problem where you have to derive the maximum likelihood estimate, it'll be pretty simple. So I mainly just want you to understand the general principle there behind maximum likelihood estimation. And so it would not be useful to have this table available, but it's just an example of the outputs of maximum likelihood estimation. So the maximum likelihood estimate for an exponential parameter is 1 over the average time, you know, as an example. So these are outputs you can get if you go through the process. So then we revisited the chi-squared test, and we used this as a goodness of fit test for our input models. And so this is a chi-squared test for an arbitrary distribution. So we think the distribution's Poisson distributed, but we're not really sure. So we're going to say, if it were Poisson distributed, how many counts would we get in each bin? And how many counts did we get in each bin? And then compare those counts together. So chi-squared is all about counts. And so the important thing to remember is how to calculate the probability that a variant would land in a particular bin in your chi-squared, and then scale that by the number of samples to get your expected counts. And then you actually have the number of counts that actually landed in that bin. If I give you a cumulative distribution function, you know that you can calculate this probability just by, if it's an interval, evaluating the CDF at the top of the interval minus the CDF at the bottom of the interval, and that gives you that probability. So you don't have to do any crazy integrals or integrating under a curve. So if I give you a CDF, make use of it to do quick calculations of this probability. Now remember to combine classes that have expected frequencies less than 5. Your goal is to use as many classes as possible under this constraint. If you cannot possibly create 2 or more bins that both have an expected count greater than 5, you can't use a chi-squared test. You have to use something else. So that's important to know too, is that when you have very few samples, if it is impossible to create 2 or more bins that each have an expected count of 5 or more, then you can't use a chi-squared test. So that's another important thing to remember. The critical value and almost all of the basic stats that you learn at this stage in your career, the stat you're calculating is a difference from the null, and the threshold value is the maximum allowable the difference for the specified significance level alpha. So if I give you an alpha of 0.05, you can look up in the back of the book and say, and I'll give you all the stats tables. I'll give you all the critical tables, just like we did on the midterm. And you just need to look up the right critical value. And if it's above that critical value, you've rejected the null. If it's below it, you failed to reject. For chi-squared, the trick is it's the number of categories you end up with after this process, -1, minus the number of parameters you had to estimate. So if you, and I told you it was a Poisson, but I didn't say what mean, then you'd have to estimate the mean in order to figure out which Poisson to use to calculate this expected value. And so that would mean I'd have 1 estimated parameter there. And so that's our chi-squared. Any questions about the chi-squared for generic distributions? Yeah. Yeah, you should know how to do the KS test as well, Kolmogorov-Smirnov test. So, because that, of course, if you can't do a chi-squared, in this class, you would go to a KS test. So you can imagine, I might give you 6 data points, and I might say, use an appropriate test or whatever, or I might ask you, like, why do you need to use a KS test? And you'd have to know that, well, if I only give you 6 data points, there's probably no way I can create 2 bins that have an expected value of 5 each, because there's only 6 there. So I could do 3, 3, you could do 1, 5. So there's no way I can, I need it basically for 2 bins, I need at least 10 data points, basically. So if I have less than 10 data points, I'm not using a chi-squared test, but I can use a high-powered test like a KS test. So then you could go and do the KS test. And the KS test, I think, is actually much easier to actually do than the chi-squared test. You just sort the numbers, and then you do a couple of subtractions, you take the maximum difference, and you're done. Whereas there's a lot more you have to do for the chi-squared test. And this is our KS test. So that's the same idea here, is that, so if I give you 5 data points, the key difference between the KS test pre-midterm and post-midterm is that you sort your data as usual, but then you run them into the hypothetical CDF, and that will turn all of your data points into a value between 0 and 1 that will also be sorted, because these CDFs are monotonic. So if they're sorted in the X values, they'll also be sorted after they get run through the CDF. And then you just do the KS test just like you did pre-midterm, where the middle row here are the CDF values of your data. The bottom row are basically 1 over n increments. The top row are 1 over n increments. You do the subtractions, you take the maximum difference, that's the statistic, and then you compare it to the table. And in this table, the degrees of freedom are the number of data points, and the alpha value, and you look at the critical, that's under the critical in this case. So any questions about the KS test for general distributions? Okay. I mentioned before, I'm not expecting you to know the Anderson-Darling test or the Shapiro-Wilk test, but just generally know that there are higher powered tests. So the Anderson-Darling test is a more powerful test than the KS test, so it can discriminate with fewer samples. The Shapiro-Wilk test is super powerful, but it only can be used with normal distribution. So just the general idea that multiple tests exist because we often have different requirements about power and the number of samples we have and so on. So questions about input modeling and sort of validating your choice of an input model. Questions online? And again, if you have any other questions, feel free to bring them up. Just kind of going through the basics here. These are the types of things like when I make the exam, I basically go through this lecture, and on every slide I say like, well, is there a question I can take out of this slide, and so on. TV and V and calibration, kind of already talked about this just sort of earlier. Validation is a type of goodness of fit. We've talked about the different ways to use different types of t-tests. We talked about power analysis to choose your number of samples. So kind of we already covered that earlier. For performance, there are point estimators, arithmetic mean, time average, quantile. Point estimators are random variables themselves. Every time you rerun your sim, you're going to get a different point estimate, as long as it has a different random number seed. So they have their own sampling distribution. And so interval estimators represent the uncertainty in our simulations. That's the reason why we need to give an interval estimate, not a point estimate, because we need to say that, when we ran our sim over and over again, we kept getting different point estimates out. And so this is a confidence interval from 10 runs of our sim, which tells us where we think the actual performance parameter is, because each individual one isn't that helpful. So that's why we generate confidence intervals. So a confidence interval is a geometric interpretation of a t-test. So it's every hypothesis that would not be rejected from the data we generated using a t-test. A prediction interval is a little bit different, where it's characterizing the spread of future outcomes. So I run 10 simulation runs, and then I can calculate, this is roughly speaking is going to be the 95, it's going to capture 95% of the next, simulation runs. So if I want to say like, so this is our measure of confidence, and this is our measure kind of risk, how far away could the next simulation run be? Well, that's our prediction interval. But as I'm running the sim runs, I'd say, well, what is the true average? Well, that's our confidence interval. So any questions about confidence intervals and prediction intervals, why we need them and what the difference between them are? Okay. So then different types of systems. We talked about this already, kind of from that homework J2 question earlier. So for transient simulations of terminating systems, the key question is how many replicates? How often do we sample this? And we know that we could do power analyses for that, but it's a simpler way to get at something very similar without formally modeling how much power we have, is to use this expression from the half-width formula and say, well, generate enough replications that my half-width of my confidence interval is sufficiently small, where sufficiently small is going to depend on your application. So it's small enough where the difference between the mean of the sim and the true mean is insignificant, not practically significant. And so that's how you set this epsilon up here. And so you can plug that into this formula here. And if you've got a standard deviation estimate from some previous runs, you've got this bound on the half width down here. You plug that into this critical Z value for the alpha value that corresponds to your 95%. So this would be an alpha of 0.05, but divided by 2 because of the two-tailed distribution. And then you can calculate the number of replications you actually need to run in order to get your half width down to this size. And you can subtract off the replications you ran in your pilot study to generate your estimate of the standard deviation. And that's a way that we can decide on how many reps we need to run. So any questions about this process? You also worked on this, I think, in lab 9. I think you had to practice this as well. Maybe it was lab 8, lab 9, I think lab 9. Okay, and then switching from that then to steady state simulations, where we do care about how many replicates, but now we have all sorts of other interesting things to care about. So how much time should we truncate to get rid of the transients? Because in a steady state sim, we don't care about the transients. We only care about estimating from this value out here in steady state. So do we want to shift the initialization bias up, like we're talking about in that question about homework J2? How long of a warm-up period do we want to knock out these data? And then once we've done all of that, we still need to answer the question of how many times do we want to run this thing? And we could run lots more replicates, but every replicate, we have to throw away this amount of data. And it might take you, a large portion of time just to get through your warm-up period. So in that case, maybe we actually do a longer execution time. So we can use less replicates and have longer times. And by having a longer replication time, the variance from our steady state estimate will be less, so that the confidence intervals across our replications will be tinier. And that is like the same effect of generating more replicates. But then the nicer thing about it is by running our sims longer, we'll actually be able to run our warm-up times a little bit longer and actually reduce the initialization bias even further. So that was kind of the key features there, is how do we choose those things. And then moving up to thinking about 3 or more systems, we've got these 3 systems. We can generate performance estimates for system 1, system 2, system 3, and then we need to rank them all together. And so if you have 2 systems, you can use a paired difference t-test or a 2-sample t-test. If you've got independent reps, paired difference if you've got the same inputs like in CRN. Construct confidence intervals, determine whether the differences include 0. If you do multiple comparisons, like you're not just comparing 2 sims, but you're comparing 3 sims and trying to rank them all. We already talked about it, how you have to use Bonferroni correction. And so we've already covered some of that. So any questions about performance estimation? Questions online? We've only got one more review topic. And that's VRTs. And so we just talked about VRTs, although we've been kind of hinting at common random numbers throughout a lot of the semester, all the way back to one of the first labs. So know the basic idea behind VRTs, that we're reducing variance in our sims so we don't have to run a lot of replications. We can do that with CRNs by running the same random numbers through multiple sims and then taking their differences and plotting out their differences instead of their absolute values. For control variates, we can measure another source of variance and subtract it out in kind of a clever way, so that our performance outputs are more due to the sim and not due to some variance in an input. We can do antithetic variates, where when we're estimating the absolute performance from one simulation model, we can run a set of random numbers into one rep. And then in the replication that comes after it, we do 1 minus all of those random numbers. And then we take the average of the 2 outputs and we do that over and over again. And we end up using those averages as our outputs to generate our confidence intervals. Or importance sampling, where we're trying to estimate the frequency of a very rare event. And so we do a type of stress test where we actually bias the input models to generate more of those rare events, but then re-weight the outputs so that when we take the confidence interval in the bizarro world where it's where the stress inputs are there, then we can translate it back into this world where we have the true input models. And so we use a likelihood ratio in order to do that. So those are basically our 4 VRTs. I've kind of beat them over the head. So I've got a couple of arena things next, but any questions about VRTs, which is kind of the last lecture topic that we covered this semester? All right, so I think the last other things here, so things to know about arena for the exam, common arena blocks that you could recognize in a flow chart, syntax for common distributions, like Expo 5 versus Expo 5, 1. Remember the 1 is that random stream. So if you want to put a custom random stream in there, if you look at the back of the Kelton textbook, there's some appendices for common distributions if you want to sort of review other examples there. How to use disk for discrete distributions, relationship between disk and cont, how to configure Arena for VRTs. So remember that Arena, you can go through and you can bring in the seeds element, and the seeds element allows you to set up for common or antithetic variants, common random numbers or antithetic variants. And then how to interpret statistics from post-simulation reports. So understand the relation between your confidence intervals and the transient replications, convert confidence intervals to standard deviation. So if I give you a confidence interval and you know how many reps, you should be able to calculate what the standard deviation is estimated for the population, for example. And so those are the kind of the key Arena things. And I think that's kind of all I've got for you. So any last kind of burning questions? If not, then I'll just give everybody attendance credit for today. And again, stage 1 opens up tomorrow. If you have any questions, feel free to let me know tonight and I'll try to get back to you. Good luck on your projects. Projects due tomorrow as well. Any other questions online? All right, if not, then I will go ahead and close out the room.